A very good evening to one and all present in this virtual platform. Let us start today's event by invoking the blessings of Almighty. I take immense pleasure in inviting the participants to this second session of the 3-day hands-on workshop on Latex. I welcome our Honorable Resource Person, Dr. Sriram Alladi, to this workshop. Now, I request Dr. Sriram Alladi, sir, to take over the session.
So I'll share my screen. Yes. Hopefully you can see my screen.
Yes,
Okay.
sir, we are
So
able to see.
let's just review what we have covered until now. And then we'll begin with some fresh content. Okay.
Sir,
Yeah.
sorry to interrupt, sir. Yesterday there was a query in the chat box which we missed to tell you. The participant was asking how to insert diagrams in the LaTeX. You can cover as and when you please, sir, when you find time. We just thought of
actually, yeah, that's a good question, actually. But there are like multiple answers to this question. So you'll have to use something called Tix. And that will take, I don't think I'll be able to cover it in this workshop. But there is a package called Tix, T-I-K-Z, right?
Okay.
And it takes some time to learn Tix.
Okay.
Maybe I can touch upon it tomorrow.
Sure, sir.
Yeah, but the thing is, Tix will require you'll have to spend some time with it. But yeah, if let's say you are doing research in graph theory, you'll need to draw a lot of graphs. So then in that case, Tix is really useful.
Okay,
so
sir.
It's spelled T-I-K-Z.
Okay.
And there are many other packages. So you can just Google about it. And another option is, so you can draw a diagram by hand and then try to attach it to this LaTeX file. And that is also a possibility. But I think if you're if your research involves a lot of diagrams, then it's actually a good idea to like sit down and learn some Tix.
Okay.
Yeah. Okay. So yes. Yeah. So this is like we talked about the basic structure of a LaTeX document. So document class, then a square bracket PDF article. So this is telling us that we intend to like produce an article, and that the output should be in PDF form. And remember that every LaTeX document has to contain this first command, right? And then there also has to be a begin document and end document. And without this, your LaTeX code is not going to like compile. Okay. And so there are many classes of articles. So you have like article, book, slides, report, beamer. So beamer is for presentation, book for typesetting books, slides for articles, and then report for thesis. And
Ma'am, I can't hear the voice.
you can't hear my voice. So I think I should be audible.
Sir, we can hear you, sir.
Am I audible?
Yes, sir. Yes, sir. We can hear
Yeah,
you.
okay. Thank you. So and then line breaks are easy. You don't have to like type any special command. You just leave a line space and then that will take you to the next line. Okay, and the third most important thing is that like any math expression has to be typed between two dollar signs unless you're typing equations. In the case of a equation, then you type like a begin equation and end equation, and then any math content is in between that. Okay. So now let's just continue with some of the examples that we were doing yesterday. Okay. So I'll go to overleaf. Yeah. So this is workshop. So this will load the document. Yeah. So you see, this is my LaTeX document that I'm currently editing. So it has like the stuff. It has a begin document and end document, and everything before that is the preamble. And then you have these packages which add extra functionality. Okay. So now let's see how we can type integrals. So this is a section, typing integrals. So one, just let's see a very basic integral. So integral x squared is just going to be x cubed by 3 plus c. So let's see how we should type that. So you want this as an equation, and then okay. So then in between this, you have to type whatever like command. So the basic command for integration is /int. Int stands for int, and then you want to integrate x squared, right? And then you need a dx. Now, the unfortunate thing is you can see that this x squared and dx are really close to each other. So one solution that LaTeX comes up with is you type backslash and then a comma. This like produces better spacing in integrals. And now this should be x cubed by 3, which is a fraction. So for fractions, we have x cubed. Yes. And let's compile this. So if you compile this, let's switch to PDF to look at our output. And so you see, you get integral x squared dx is x cubed by 3 plus c. Okay. So let's, and you can see that this is there's no equation number here. So what we can do is, if we want, we can add an equation number as well. So let's go to overleaf, switch to editor. Okay. For some reason, it's not producing a number. Okay, we'll come to that later. But if you don't want numbering, this is what you do. You include a star and you compile this. So this gives you integral x squared dx is x cubed by 3 plus c. So let's see. So the basic syntax is easy. So slash int and then whatever integrand, and then you have the dx here and a slash backslash comma so that you improve the spacing between your integrand and dx. So let's look at like more examples. So let's try to type a much more complicated integrals. So here is 0 to infinity e to the power of e to the minus x squared dx. This is square root of pi. So let's type this equation. So you have a begin equation, end equation, and then int e raised to minus x squared and now you need limits. So if you look at this, you have a lower limit and an upper limit. So the lower limit, you have underscore 0, and then the upper limit, infinity. This has to be square root of pi. So this is what it is. And see, it is numbered. Okay. So the first equation, we suppress the numbering. And now here we are actually including the number. So now, let's say if we include numbering for the first equation. So this becomes the second equation, and this is automatically the third equation. The important thing is you don't have to do this manually. So what about other types of integrals? So let's include a subsection here. Or multiple integrals. So let's look at an example. So like a lot of multiple integrals come up in physics. So I picked one example from physics. So I need to type the following equation. So if you've taken a physics course or some fluid dynamics course, you'll recognize this as Gauss's law of electric flux, right? So if you integrate the divergence, so E is a vector field, and you look at its divergence, you integrate the divergence over V, you're going to get, that is the same as the flux of the vector field over the surface, which bounds the region. So you don't have to know this. Let's just try to type this. Okay. So like, what is the problem here? So the problem is there are multiple symbols that are not available to us on our keyboard. So how are you going to type some letter with an arrow on top, right? And this is the gradient. How are we going to type that? ds and dv are easy. And then how do you type triple integrals? And also how do you type this double integral? So let's attempt to type this. So you need a begin equation and an end equation. And your content goes between these two. So so what happens is now let's try to type this triple integral. Int is not enough. So the idea is you have three integrals, so 3 ins. That will give you a triple integral. That's the command. Underscore v, that will give you this v here. And then we need to see how to type this gradient, and the symbol for that is nabla. So you don't have to remember all these things. So it might seem very intimidating in the beginning, but you can always use Google. Just type the symbol, a latex symbol for gradient, and Google just give you the answer. And then as you become more familiar with latex, you'll automatically remember these things. So it's not a big deal. Okay. And then we need a gradient. So this nabla, and then we need to produce this dot here. So for that, what you can do is C dot. And then E. But unfortunately, if you look at E here, it doesn't have an arrow on top. So what we do is, but now if you see this, so the spacing, there is too much spacing here in this output preview that is shown to us. We don't want that. What I actually want is great. Yeah. Is there some question? Okay. So grad.e. So there's too much spacing between the grad and the dot. So what I'm going to do is this nabla. Yeah.
58. 1.
You already.
Oh, 2 opposite present, 3 present. Well, 4, 7.
Okay. Yeah.
7,
so this
8.
Is what we. And now we need a DV.
8 to 9. 4, 7 is there?
4, 7, 8, 9.
11, 12.
I think someone is talking. Is there any way you can mute them?
18, 19.
Lakshmi ma'am, please mute yourself.
Okay. So let's compile this. And we'll look at the PDF form. So you see what we have here. Okay. And let's, this will show you the PDF. So there's at least one half of the equation we are done. So now let's go to the double integral. So the solution for the double integral is easy. So we need only 2 integrals, and then we have to type E dot n. And n ds. This backslash comma is just to produce proper spacing. The technical thing has no other function. And so now what we want is we want a sort of hat on top of n, because n is actually a unit normal here, right? And so what we do is hat n. That does the trick. Okay, but unfortunately, we're missing a couple of things here. So we want integral s. So the bottom, we want an s at the bottom. So subscript s, that adds an s. Okay. But this doesn't tell us that this is a surface integral. So what we'd like is and let's compile. So you see we have an error. So what is the reason for this error? So the reason is we need to include this package. So there is a package for this, and I've included it here in my sample slides. Go to my sample document here. So there's something called OINT. ESINT. So what I'm going to do is include this package ES, so that I can produce this integral like with a circle. Let's come. So you can produce some pretty complicated integrals using Latex. Okay, let's look at another integral. So all of you must know what the gamma function. So this is like a single integral. So I'll include that here. So you have like a begin equation and an end equation. And so then gamma of x, this is integral 0 to infinity. T to the power of x minus 1 slash dt. So you remember like what we discussed yesterday, that gamma is a Greek letter. So there's like no key that is available on your keyboard to type a gamma. So what you have to do is slash gamma is the command to type gamma. And then we have this integral, 0 to infinity. So 0 and infinity are the lower and the upper limits. And then you have to type the integral, e to the minus t. So that is e. And so this is the command for e to the minus t. E followed by this symbol here, and then square bracket minus t, and then t to the x minus 1, a backslash comma dt. That is for the spacing. Okay. Are there any questions about this? So again, like this might seem very intimidating if you're seeing it for the first time, but it's actually not that. With practice, you'll become familiar with it. Let's look at some derivatives. So let's look at the derivative of sin x is cos x. So let's see how to type that. So if you don't want it to be numbered, you need equation star. Otherwise, this is fine. So if you've taught a calculus course, or if you've taken a calculus course as a student, so there are many notations for the derivative. There's the prime or dot or d by dx. So let's try to type d by dx of sin x is cos x. So if you think about d by dx, so it looks like a fraction, right? So this gives you a d dx. This is sin x, and this is cos. We saw how to type sin x and cos x yesterday. It's what the command is. What do you think it is? So you just compile this, and this is your output. D dx of sin x is cos x. So let me show the. So this is the command. So ddx, you just use, it's essentially just a fraction, and fraction d dx sin x, and this is cos. And to type sin x, you have the command is /sin x and /cos. And let's look at the output. So this is the output. So what about higher derivatives? So let's look at an example. So suppose let's look at e to the ax, and I want to type the nth derivative of this. So the idea is you have fraction d dx, but now you need the nth derivative. So d to the n, so fraction d to the n, and then d to the nx, e to the ax. This is going to be a to the n, e to the a. Okay. So now let's try to compile this. Unfortunately, this is not right. So yeah, this gives you what you. So the nth derivative of e to the ax is a to the n e to the. So just you can also like type use the prime notation. So you have sin x, and the symbol for prime is just prime. This is cos x. So if you compile this, you'll get what you expect. So pretty much most of your elementary mathematics that that you use, you can type using Latex, and actually much more. Okay. So let's talk about functions, right? We saw how to type some elementary functions, right? Like sine, cos, and you have built-in commands for this. But in math, we actually study like functions whose definitions are much more complicated, right? So let me go to my slides. Yeah. I'm sure most of you must have seen the definition of mod x in high school. So this is the definition. So mod x is not given. So this is an example of a piecewise function, right? So mod x is x if x is bigger than 0, and minus x if x is less than or equal to 0. So depending upon what condition x satisfies, the definition changes. So how am I going to type something like this? And if you think about how to type this using Word, it's not that easy. But with LaTeX, you can actually type this easy. So let's see how. piecewise function. So sorry. Equation star, because I want this as an equation. And I don't want it to be labeled. So mod x. Okay. So how are we going to, what is the problem here? How are we going to type like the vertical lines? And that's quite easy because it's just available on your keyboard. Right? So you have two vertical lines. In between that, you have to type an X. And that's also easy because X is available on your keyboard. And now, if you think about this, this is a case by case definition, a definition by cases. So we're going to introduce the cases in mind. So if you look at this, this is saying X, if X is positive. So let's see, if X is greater than 0. And we'll have a problem. And then we have to go to the next line, minus X, if X is less than 0. In fact, the first problem is, if you see this if here, there is a space between the X and the if. And here, like in the preview that like overview has provided, there's no spacing. And that is because usually in the math mode, spaces are suppressed unless you explicitly type spaces. So what I'm going to do is, I want this if as a text. Then here I'll introduce two spaces. And now this is okay. The same thing here. Okay, if X is positive, yeah. So now we actually need greater than or equal to 0 or less than or equal to 0. Doesn't really matter. And there is no greater than or equal to symbol on your typewriter or on your keyboard, right? And so what you do is, the symbol is like, the command is what you think it is, greater than or equal to. And if you want less than or equal to, it is slash less than or equal. So let's compile. Yeah. So this is how you type a piecewise function. And the only thing is, if you want further space between the X and the if here, so remember we talked about this yesterday, you can introduce a hedge space and maybe 3 millimeters, so that the ifs align with each other, and we get this. Okay. So this is our first example. So you want to type a piecewise function, you need the equation environment, and then you also need to use begin cases and end cases. And here you have these double backslash that helps you to, the double backslash actually takes you to the next line. Okay. So let's look at another example. So I want to define a function from R to R by f of x equals 1 if x is irrational and 0 if x is rational. So how do we type this? So again, this is a definition by cases. And so the idea is the same here, except here now we need to produce this arrow, and that's easy. So let's find. So define f from R to R. I begin equation. So I don't want to refer to this later, so I'm not going to number it. So this is the first thing is we want f of x. So typing that is easy. So it's just f of x. And typing equal to is easy. It's just available on your keyboard. And then you have because this is a definition by cases, you need to use begin cases and end cases. So what I'm going to do is, this is defined to be 1 if x is irrational. And then in the next sentence, you want 0 is rational. So the problem now is, how do we go to the next sentence? So the command is double backslash. And now let's compile. So you see, it produces what you want. Okay. So now there is a problem. So if you look at the R here, F is defined from R to R. If you look at a lot of math books, they use this bold font for R. So you have, it's not exactly an R. This R is like very different from this R, right? In appearance. So to produce this R, what we do is we have to include a package. You include something called AMS sim. So now what you do is you type math BBR and math BBR and you compile this. And let's look at the PDF. So you get what you want. So this is how you type like other symbols. So you include the AMS sim package. So now you should be familiar with how to type a piecewise function. Okay. So are there any questions until now? Okay. So now another object that comes up often in math is like that of a matrix, and also sometimes you like an associated object is that of like a determinant. So how do you type matrices and determinants in LaTeX? So let's look at that. I need to go to my editor. So typing matrices, that's us. So the command is as you'd expect it to be. So you have like many like possible ways. Sometimes like you have like matrices with square brackets. Sometimes you use simple brackets, and like you use vertical brackets for like determinants, vertical lines for determinants. So let's see. So let's take a very, very simple matrix and see how to type it. So like, what's the most basic, one of the most basic matrices is the 3 cross 3 identity. So let's see how to type it. So you can see that its entries are 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay. But now, if you, there's a problem. So there's no space, right? So now the columns are not separated. So I'll include an ampersand.
శివకుమార్ ఈ పిల్ల నా స్టూడెంట్ కాదు కానీ తెలుసు వేదవతి స్టూడెంట్
Lakshmi ma'am, please
Yeah.
mute yourself.
Okay. And let's typeset this. This just gives you like an array of entries, but it doesn't give you the brackets that we have, right? So for that, what you have to do is you type P matrix. Okay. And this is compiled it, but if you use an ordinary editor, you're going to get a mistake. The reason is because this is like a math expression, and this has to be in math mode. So it has to be either between dollar signs or part of some sort of equation in math. Yeah. So now you, yeah. So 1001, 010, and 00. So it's just like how we typed a tabular column yesterday. You might remember like how we typed tabular column. It's pretty similar, right? To go to the next row, you need two backslashes, and then adjacent entries in adjacent columns are separated by an and symbol. Okay. So let's look at, this can also be a part of an equation. Sorry. So I2 is begin. Let's use P matrix. And then what you get is 1. So again, the spacing is off. So you need to separate the column entries. So you need an and. So you see, you get an identity. So now here you notice that we just have like ordinary braces instead of like square brackets. Okay. Yes. How about determinants? So let's look at a 3 cross 3 determinant. So, or a 2 cross 2 determinant. So if you look at like how we like represent determinants, someone is talking in the background. So I'd request you to mute yourself. Okay. Okay. So let's see how to type a determinant. So here you just have to use vertical lines. And so the again, the command is what you expect it to be. V matrix. V as in V for vertical. And so now, let's see, determinant of, let's, yeah. Okay, that's because I think there was a problem with my connection. Yeah. So I hope everyone can see my screen now. I'll go to overlays.
Yes, sir.
Yes, sir.
So we were talking about how to type determinants, and yeah, I see that I lost some of my work. So yeah, just to recall, like if you think about how we type a determinant, we use vertical lines instead of braces or square brackets. So the first, let's try to type determinant of A, B, C, D. A, B, the next line is C, D. But now we need spacing between the A and the B. Yeah. And this determinant has to be, in fact, this is by definition AD minus BC. Okay. So now what we can do is, let's just see how to type a more complicated determinant. Begin. Let's look at the definition of a 3 cross 3 determinant. So the first entry is A11. So you want A11. So you need to produce like A and 11 as two subscripts. So this is the command for that. A underscore and then 11 within brackets. Then A12, A12. So then the next one is A21, A22, then A3, then A31, A32, and then A3. And all these things, the columns have to be separated. Okay, so what I'm going to do is, yeah. So now this is, as you all know, this is just A11 times A22 minus A into A33 minus A32 into A. Okay, this should be A23. I've made a mistake here. Minus A12 into A21, A33 minus A23, A31 plus A13, A21, A32 minus A22 So let's compile this. Go back here, just compile this. And I'll look at the PDF. So this is the output. So try to do this with Word, and you'll see that it's much harder. Okay. So another thing that you see, if you have ever read a math paper or a math book, you'll see that theorems are usually in italics, and they actually label. They say, okay, this is a theorem, this is a proposition. So how do they do that? Right? So there is a package called the AMS theorem package. So I've included that here. So let me include that separately. So use package, AMS theorem. And now what we're going to do is we're going to type like a theorem. So for that, what I'm going to do is, let's start a new section that is about typing theorems. Theorems, lemmas, and definitions. So there is a AMS theorem package. So what you can do is begin theorem, end theorem. So let's look at state some like famous theorem in math. So for example, Pythagoras theorem. So the syntax here is begin theorem, and then you have to end this with a end theorem. Let's just like begin equation and end equation. And this is the name of the theorem. Okay, Pythagoras theorem or Pythagoras theorem. And then now the statement in between this. So the statement is in any triangle, any right triangle, the square of the hypotenuse is equal to the sum of the squares of the other two. Let's try to compile this, and most likely it's going to show an error. The problem is it doesn't recognize this begin theorem and end theorem. See, the output also like it's not nice. Like what I'd like is theorem, Pythagoras theorem. So what I have to do here is I have to use a new command. New theorem. So the first thing should tell me here I have to type theorem. And this is how it will appear. And we'll come to this part later. So now let's type. or compile it again. Yeah, so you see the difference. So theorem 1, Pythagoras theorem. Yeah, Pythagoras theorem. So see, the statement is in italics and it's neatly labeled, and there is numbering also for the theorem. So in any right triangle, the square of the hypotenuse is equal to the sum of the squares of the other two sides. Okay. So let's type a different theorem. So begin theorem here. So some other.
Sir, can you show the use package, sir?
Can I show the
Use package, sir. For the AMPS theorem you have used, sir. Can you show that once again, sir?
Okay, just one second. Oh, you. Just a second. Yeah. Use package AMS theorem. AMS THM.
Thank you, sir.
Yeah. So let's see another theorem. Okay. So this is so the theorem name is optional here. The stuff within the square brackets here, it's not necessary to include a theorem name. So let me talk about some other theorem. Any sequence of real numbers. Sorry. Any bounded sequence of real numbers has a convergent subsequence. Let's combine. So you see, and it automatically numbers it also. And remember, the statement always has to be in italics. And it does that as well. You don't have to manually do it. Whereas if you're using a bird, you will have to write it out in italics each time. And it's very cumbersome, especially if you're writing very lengthy papers. You don't have to do that here. Okay, and the same thing can be used for lemmas as well. So let's see. We have a lot of definitions here, right? So if you see, this is a definition. So let's convert this to a definition. This thing about the determinant. Okay. I'll go to my code. So I just begin definition. End definition. And this is a definition. So now what I do is, I have a statement. So the determinant of a cross 3. If you want multiply, you have to type times. As follows. And let's compile this. It's going to give you an error. The reason is it doesn't recognize this begin definition and end definition. So what we have to do is we have to tell it that how to recognize this command. So we go here and here we type new theorem. So we are going to type the first bracket contains definition. That is what we are typing. This is how we'd like it to appear. And now let's go ahead and compile. Sorry, there's a spelling mistake, so it flags this. This should be new here. So you see. So let's go to the PDF. Yeah. So you see it comes out nicely. So now suppose you want just to get familiar with this, let's use this again. Definition. So the determinant of a 2 cross 2 matrix. 2 times 2 is defined as follows. And so let's compile this. And see, now, like, the good news here is, so this is our first definition. Now this is the second definition. And it automatically changes the numbering. You don't have to do this each time. Again, if you're writing a long paper with a lot of definitions and theorems, you don't have to do the like numbering manually. LaTeX does it for you. So that's like one of the advantages. Because if you're going to do it manually, most likely you're going to make a mistake. In fact, like almost every time I make a mistake when I manually number stuff. Okay. Right. And so the same thing is, we can also like label examples as well. So if you see, we have like discussed a lot of examples. So let's, so for example, this is an example. So I can say begin example, end example. And let me compile this, and it's going to produce an error. So the error is it doesn't recognize this begin example and end example. So we have to tell it like, so now here what I want is example. This is what I'm going to type, and this is, I want it to appear as example with a capital E. So let's recompile. So now it works. So this is example 1. So example 1, so I can write, this is an unordered list. So then the next one is example 2. This is an unordered. This is an ordered. And now let's compile it. Okay, so one thing is this is in italics, and if you want to, you can that it is not in italics, because usually only theorem statements are in italics. But that's okay. We don't have to worry about that. So another thing that we talk about is corollaries. We can type corollaries as well. So some corollary, like, okay. So every sequence of real numbers that is bounded below has a greatest known non-empty sequence. So let's compile this. So again, it doesn't recognize this. So we have to go back and tell it, okay, this is what I want. And so it's going to number. So now this will be okay, and it will number the corollary as well. Yeah. Yeah. So now you see corollary 1. Every sequence of real numbers that is bounded above has bounded below. Every non-empty sequence of real numbers that is bounded below has a greatest value. And now you can type definitions. Okay, we saw how to type definitions. Okay, so another issue that comes up here is, so ideally, this is theorem 1, theorem 2, and this belongs to section 12, right? So we'd ideally like this to be numbered as theorem 12.1, and this to be numbered as theorem 12.2 and corollary 12.1. So then what we can do is, let's go back to the code. I can type section here. And this is for the sake of numbering. And let's compile this. So you see, now example 3.2, 3.1. And so if you come to the theorem here, so these definitions are a part of section 11. So instead of definition 1, now we have 11.1, definition 11.2, theorem 12.1, 12.2, and corollary 12.2. Okay.
Sir, I have a doubt, sir.
Yeah.
What if we need to get corollary 12.2.1, sir? Because if this corollary, if I'm typing a corollary beneath the theorem, sir, then I need to have the corollary numbering as a continuation of the theorem, sir.
Okay, so that, I think what you can do is, let me see, that's a good question actually. So, yes. So instead of corollary here, you can write theorem. And this should be the, and switch to PDF. Yeah. So you just go back to the code. So now you see you get 12.2.1. because this is following theorem 12.2. So I'll just go back to the
Thank
code.
you, sir.
So this corollary is actually followed by a theorem. So so in this square bracket, you just type theorem. Okay. Right. So that means that like whatever number you have for the latest theorem, the corollary will be like following them. So as you said, you get now, I think 12.1.1. Okay. So now another thing that we do in math is we actually type proofs, right? And so AMS math actually provides, I think, a proof environment. So for example, let's say we want to type this proof. So first, you need a statement for a proof. So let's include this. One of the earliest proofs that we see in school is square root of 2 is irrational. Right? And let's see how to type the proof of this. So this is the theorem. Theorem 13.1, square root of 2 is irrational. So typing a proof is easy. So what you do is you type a begin proof, end proof. And it does the job. And at this square bracket, this will actually tell you that you have reached the end of the proof. Some people use QED also. And if you want, you can like modify the proof environment so that you have like, it ends with a QED. So let's just type this proof. Suppose not, then there exists two integers, positive integers. M and N, such that fraction M N is root 2. Okay, squaring we get star M squared is 2M squared. So let's compile this and we can finish the proof. I don't want to. So you see, so this neatly gives you the proof environment, and then the square bracket indicates that you have reached the end of the proof. Again, I don't think Word offers such a facility. Right? Okay. So how much time do I have?
10 minutes, sir.
10 minutes. Okay. So now another thing that we actually do in math is we actually keep, so if you've ever used a math book or a science book, we like refer to results that we have like previously established, right? So like for that, what we have to do is we have to label these results. So for example, here is a theorem. So what I can do is I can label this. The reason is now I can refer to it later. So label. So, and the stuff within, you can give whatever name you want for the label. Important. So what I usually do is, this is a theorem, Python. So now what we can do is by Pythagoras theorem or by reference. So I want to refer to this. So the symbol for labeling is /label, and within curly braces, whatever like name you give it. And if I want to refer to it, /ref, and within the curly brackets, whatever label that I used. So now let's recompile. So by 12.1. So now if you want, so if you click on this, it will go to the theorem. Okay. So if you want to create a link, you have to include, I think, a package called hyperref. So let me do that. And now let's compare. So you see, now I click on this, it takes me to theorem 12. So here, it's not that useful because both of them are like in the same section, but let's see. Suppose I type by theorem ref theorem Pythagoras, and let's compile this. And let's go to the PDF. So here I have a reference to 12.1. I click on this, it takes me to Pythagoras theorem. So the same way, so this again in Word, you will actually like creating hyperlinks is not that easy. So you'll have to convert it to a PDF, and then in the PDF, like you'll have to like include hyperlinks. Like I don't know actually, but it's what I know is it's fairly tedious. But in LaTeX, there's a package, and using that package, you can easily do. Okay, and you can do this for pretty much anything. So let's go back, switch to the editor. So let's say I want to include a label. I want to refer to this definition. Definition determinant. It can be anything. I've just included definition here because it's then easy for me to remember what name I've used. So if I want to use it here, so by theorem this and definition. So let's compile this. So by theorem 12.1 and definition 11.2. So if I click on this 11.2, I get this. Okay. And we have all these examples here. You can create labels. It's actually a good idea. If you're going to refer to like something later, it's always a good idea to create a label. So for example, now You can also like label equations. So let's create a label for this equation. So this function f of x is 1 if 1 is irrational, 0 if x is rational. So this is a Dirichlet function. Okay. So now I've created a label for this. And what you can do is you can refer to this. Let's go to the PDF. Yeah. So by int. So it takes you to int. Okay. And you can label a definition or a corollary or anything. So just slash ref, whatever within the curly braces, you enter the name, the label name, and then when you slash label and enter the label name, and then slash ref, the name of the label that you have used. Okay. So are there any questions? Okay, just to summarize what we have done, let's look at, let's try to type a theorem. Taken theorem and theorem. So I'm going, all of you are aware of De Morgan's law. So this is from set theory, right? Like very basic set theory. So for any two sets, A and B, we have begin equation, end equation, uh, okay. So now, if you remember, I hope all of you remember De Morgan's laws. There are like two of them, but they're sort of equivalent. So A union B complement is A complement intersected with B complement. So union, if you want to type union, this is the symbol in latex, sort of a cup. And complement, you can type a C or a prime, and then intersection, you have cap. So let's typeset this. Let's see, this is De Morgan's law. This has to be capital. So let A and B be two subsets. We have A union B complement is A complement intersected with B complement. So now let's label this because we'll refer this. We might refer to this over and over again. Theorem, you can say De Morgan. And maybe I'll have to refer to this over and over again. So the equation De Morgan. Okay. And so now suppose I can by theorem ref De Morgan and equation ref. So somehow that reference to De Morgan is missing. So let's see. Let's use EQ. If you want to use refer to equation, sometimes you can use EQ. Okay. I have to label this first. Only then I can refer to it, right? Yeah. So I'm labeling this equation with equation De Morgan. So that now I can refer to it. So now let's compile this. Yeah. So 12.3 and then equation 9. Okay. I think I'll stop here for today. Maybe in tomorrow's class, we can touch upon like some other topics. So I'll talk about like how to like prepare a presentation using Latex. So I don't think I'll have time to talk about text, unfortunately. So using text, you can produce diagrams. And then another thing that we can talk about is like providing references. There's something called BibTeX, right? And so many of you will be writing papers in the future. And so you'll have to prepare a sort of bibliography, right? And for that, you need to use like a tool called BibTeX. Okay. Shall we stop here?
Yes, sir.
Yeah.
I thank you so much for the informative session, sir. I'm sure that this session will help the participant to understand the tool Latex from the fundamentals. Now I request the participants to clarify their doubts if any. Participants are requested to fill the feedback forms through the link posted in the chat box. Thank you, sir, for sharing your knowledge and time with us. I also thank the participants for their active participation in the workshop. I invite all of you to attend the concluding session of the workshop tomorrow at 3 p.m. Thank you all.
Sir, I have a doubt, sir.
Yeah.
Sir, in the first, we are typing that new theorem so that we get two brackets, no, sir.
So let me just go back.
Yes, sir.
Yes. Yeah.
We are getting a two curly braces, no, sir. But while typing, we get an option of three curly braces. What is the third one, sir? Why do you use for that one, sir?
This third one, the section.
No, sir. No, sir.
Yeah.
Can you just type another in next line new theorem? Yeah, sir. Here we get three curly braces, no, sir.
Here?
Well, the second one, sir.
No, you're getting only two curly braces and one.
Yes, sir. And one square braces in the middle. What does that mean, sir? Is that the same what we have used
Yeah, it's the
previously,
same.
sir?
I don't think the order here is important.
Okay, sir. Then what about the new theorem styles, sir?
Like I don't know. So that probably some other package.
Okay, sir. Thank you, sir.
So there are many packages that do this. So there is something called N theorem that also does something. Sometimes you can, like what you would like is you want your theorem in a box or you want it to be colored. So you can, this is very flexible. So what I've done is only like a very basic thing. But if you want, to do like additional stuff with this, then you'll have to do some work or maybe use a different package.
Thank you, sir.
Yeah. Okay. Are there any other questions?
Sir, we can conclude the session, sir.
Okay. So let's stop here and we'll continue tomorrow.
Yes, sir.
Yeah. So can I log out?
Yes, sir.